Hey folks, what's up? This is Junchan, back streaming in 2021, still on a streak of, I think, about 3 weeks streaming every day. And I'm shifting a bit my schedule and habits. This could be a temporary thing. It will be a temporary thing because I am starting full-time work in next Monday. So I guess I'm feeling the pressure of not having or having less time to stream, and new ideas are popping up. So as you can see with the title, we're shifting our focus quite a bit. And I'll put this in our open workbench for now as a unscheduled event, let's say, or series. What we're looking at is implementing or testing what does doing the NBody simulation in Haskell for the GPU would look like. So, okay, I'll start with my disclaimer. This is about learning in the open. So I'm not an expert, but I'm not bad at learning. I was a teacher also in my career. So hopefully the way that I approach getting up to speed on a problem like this will be of interest to other people. But my style is, I guess one way to describe it, I said that I like to follow tangents. It could be described as a breadth first learning style, meaning I don't necessarily try to go as deep as possible from the get-go. I actually like to follow tangents. And you could argue that there's a good theoretical reason to do that. Maybe something like avoiding local minima. But I'm not going to get into that right now. Our other series, if you haven't checked it out, is us implementing the chronofold data structure on purescript. And we got to a milestone yesterday where you got a properly converging implementation. So it's not fast or anything, but actually, that means I can check implementing the CT merge algorithm here. I forgot to do that. So we were looking at performance, and I continue streaming, and I'll go back on stream this afternoon at 5 p.m. my time. But now it's 1 p.m. my time, and I was thinking about this, and it really came up as something that was probably worth streaming as a kind of self-contained series. And so let's get into what that means. So let me see. How could I explain this? I probably need to unpack this first. Let's unpack this as a... oh, right. Got a problem with our keyboard layout. So sorry, that's a little bit of housekeeping thing here. I've got some trouble keeping Windows to be in the right keyboard settings. And that's not great. It's very uninteresting compared to what I was going to talk about. So I'll actually add a stream marker here, hoping that maybe this could be edited out in some future work or a parallel universe. Soon.tm, right? And okay, I'm doing this off screen, but maybe I should do this on screen. So this way at least you see me struggling with this thing. It would be in the regional settings and language. And I'm supposed to be using a Apple keyboard, but it should be United Kingdom. And if it's not, then it means that I can't. Hey, just kicking it seems to have done it. So there's some weirdness going on there, but we are not going to spend more time on it. We're just going to be proceeding forward. Thank you, IT gods, to allow me to proceed without wasting more time on this. Okay, so what do I mean by all this? Well, so the NBody problem is a physics simulation problem, and it's something that's interesting because it's one of these problems that doesn't have, let's say, an easy theoretical formulation. I mean, yeah, or an easy, it doesn't have an easy theoretical, let's say, solution is maybe a better way to put it, which means that it's easy to write an equation for, so NBody means what? Means that we have a lot of different, basically, let's say, planets that therefore all have a gravitational pull and are moving into the same universe. And so they're all pulling each other. And an approximation of that is that, you know, like you have a big planet and, let's say, a moon. And so the big planet's weight dwarfs the moon's weight in such a way that you could think of it as actually the moon is going around the planet, right? But in reality, the moon is also exerting gravitational pull on the planet. And that's the two-body problem with just a planet and a moon, for instance, right? Or, in fact, just a planet and you, like a person on the surface of the planet, being weighted down and attracted to the planet down, right? Well, in fact, you are also pulling the planet, but that's so small, very negligible. It's a kind of an epsilon that we can sort of, you know, approximate away or not even think about. But if we actually try to tackle the problem really soundly or completely, then we need to take care of the fact that it's not just the planet attracting our body, it's actually also our body exerting like a tiny minuscule amount of gravitational pull on the planet. And obviously a moon has a more significant pull. And then when you start throwing n-bodies, which have potentially more equivalent masses, and distances where they can actually exert also a gravitational pull that's more that's stronger. We have a inverse square of the distance decay of the force, right? So if we're away, then we are actually the gravitational pull diminishes at the rate of the inverse square of the distance. So let's see what Wikipedia says about the NBody problem and see whether we've covered most of the context here. The problem of predicting the individual motions of a group of celestial objects interacting with each other gravitationally. Solving this problem has been motivated by the desire to understand the motion of the sun, moon, planet, and visible stars. Right, and well, in something worth mentioning, this is in fact a classical physics problem. We don't even need to introduce more sophisticated physics to actually already have trouble solving the issue with a simple equation. Basically, usually, and that's one of the many mathematical and physical problems that is better addressed by a computational approach, where we're actually going to put in the equation as much as we can inside some code and get the computer to actually estimate, in this case, positions and trajectories of celestial bodies or just bodies. So let's see, NBody choreography. I like this. That's nice. A solution in which all masses move on the same curve without collision are choreographies. Oh yes, yes. I think I remember seeing there's beautiful animations of that actually, if I remember correctly. NBody choreography, and I'll be right back. And I realized I also jumped on stream without doing much checklist things, and that means that there's no music, for instance. So let me fix this, even though it's displaying music on the waiting screen. So let's do that. And then I need to connect to Chatty, and that's done. So that's good. And hey, how about we pick up another station today? I'm thinking maybe... How about ambient? That would be good for like a space thing. And I'll be right back. And I'm back. And I'm trying to hear whether the music is playing or not. With ambient, it's going to be possibly tricky. Oh, there we go. Okay, so NBody choreography, and I wanted to see some videos of that. So let's go for the video. 8 body Newtonian choreography. That sounds great. There we go. The type of figures that the NBody problem can generate. And that's with right, eight bodies, and that's interesting. NBody orbits. What do we have here? Oh, we have a succession of problems. Okay, so that's the 2-body problem, and then right, 2-body problem, but this time with a sort of a different symmetry here, which yields what look like elliptical orbit. But check this out. 3-body problem. And we're starting to get like really interesting shapes, aren't we? This I don't think would qualify as a choreography. So this is a figure 8 choreography. So here we have 3 bodies that are set in such a way that they actually look like they're following each other in a figure 8. And here we start getting into n being here 1,000. So we start to increment the value of n, and we get some quite interesting things, right? And so I think this is great and very pretty. And but it's not the only thing that interests me in this. One of the maybe more long-term aspects of something that's interesting me is that this is basically what you could call a layout algorithm. And so it really says, well, I have n things, and they have some parameter, and this parameter in this case is only their weight and their initial position. And from there, I define what the next step is going to be, right? So that's really the essence of a simulation, but that's also the essence of a layout algorithm, right? And in fact, here's something that I saw some time ago, which is what, paragraph Excel? Is that, maybe that's not it. Maybe it is. It's graph layout GPU. Paragraph L. And so this, now we're starting to look at the GPU part of all this, and also the layout part of all this. So graph layout is one of these problems that are generally solved by a physics simulation, in fact. And so there's a lot of graph layout algorithms. And one that's really common is this what's often called force-directed graph layout algorithm. And force-directed, in fact, is a hint at the fact that there's some physics going on. And it's not, I mean, it is, in fact, some approximation, a subset of the NBody simulation problem. And these people here, Tao Lin and Bawei Chen, have implemented a JavaScript framework for computing this force-directed layout graph in WebGL. So not only on the GPU, but on the GPU from your browser. And some folks have done a comparison of layout of graph layout algorithm, actually, I think on the awesome observable HQ. And let me make sure that I have paragraph L in the search query here. This might be it. I think it is it, yeah. So here we have a typical example of a graph. So this uses a bunch of pretty cool, I would call best-in-class tooling for this type of representation. So D3 and Observable HQ, actually built by the same developer, Mike Bostock, which I think now might be fully dedicated to Observable HQ, but built D3 famously as a New York Times data visualization developer. And that picked up wildly. It's a really interesting take on declarative graph, or declarative data visualization. And so, in fact, D3 means data-driven documents, I believe. And Mike Bostock then founded Observable HQ, which is actually a variation on a concept that existed for a while in the programming world, and even more so in the scientific programming world, and now increasingly in the data science programming world, which is the use of what's called programming notebooks. And Observable HQ is a programming notebook, so allows to, and one of the earlier iterations of that from Mike Bostock himself was Blocks. And Blocks is this website where you can actually sort of showcase your D3 code. And that's pretty awesome. And but combined with this, one of the key open source player in the programming notebook world is Jupyter Playbook. And right, you see the tagline is to develop open source software, open source standards for interactive computing. That's one of the key points here. So you could say that notebooks are in the lineage of the REPL. It's a really super powered up REPL. And as I said, very much used in data science and in science in general. But Observable HQ, well, is an evolution from that, an evolution that actually you can trace to the Jupyter community. And that's something called Reactive Notebooks. And it was, I think, first experimented with the Python language, which is really the basis or one of the primary languages for Jupyter, even though, in fact, many more language implementation came out of it, including a Haskell one that I'm supposed to do a blog post about, and which I will. And there's been, I think this came from a conference, the Future of Notebooks in 2018, and JupyterCon, and the number one complaint about Jupyter is that notebooks have tons and tons of hidden state that's easy to screw up and difficult to reason about. And if you're a functional programming head, then, you know, like your I don't know, endorphins or like all of these hormone cocktails are flowing to your brain right now. You're like, hey, I know this language. This is functional things. It absolutely is hidden state and difficult to reason about. So you could say, you could argue that reactive notebooks are the proper sort of, how would you say it, the principled evolution of programming notebooks. And I'm really interested in this. I think this actually hints at the future of programming. So really, I think all our IDEs will be like this, basically, in the future. And the main problem, or a simple way to explain it, is that if you run your cells in the wrong order in a Jupyter notebook, you get different results. And that means that in practice, you basically have to run your notebooks from the top pretty much all the time. And that's just, well, that's a dependency tracking problem. That's also an incremental state management problem. And it's a computational graph problem. And all of these things kind of somewhat converge, in my mind at least, to sort of similar solutions like build systems and graphs, in fact. And so observable HQ, to pop back the stack, except I'm going to keep that on because I want to copy those tabs. Observable HQ is a reactive notebook for JavaScript. So Mike Bostock implemented a runtime for a subset of JavaScript language that's actually able to do all of the dependency tracking such that you can run things in various order and the notebook is smart enough to execute only what's needed. So this is kind of best of breed in terms of the notebook technology. It's unfortunately, that hasn't been generalized necessarily to the multi-language, to sort of a polyglot implementation, but it's very worth looking at because, well, JavaScript is a ubiquitous language, right? Which is why I like programming in purescript, by the way. Okay, but now we're looking at Haskell, the venerable ancestor of purescript. And popping back the stack, we have this notebook, and in here we have the paragraph L layout algorithm, which renders in 235 seconds compared to, let's say, the basic Fruchterman wrangled in the CPU, which will render in 1,000. So we've got a, I don't know, like a 5-time increase, 5x, and for Atlas 2, it does better. It must be slightly optimized, but this runs in the CPU, whereas this runs in the GPU. And look at this second render. It means like we're not 10x faster than the naive Fruchterman wrangle implementation, which, if I rerun it, runs in the same 1,000. So maybe probably because that was the initial time in compiling the GPU code in the GPU. So once it's compiled and the pipeline maintains the fact that, hey, we're not going to need to recompile this program, so it's available already for the GPU to be shipped to the GPU right away, and then we get that 2x increase already. So that's pretty awesome, and that means that we can do things like look at larger graphs, and like this one, for instance. And that's in the web browser, right? So that's pretty awesome. And so what does it mean? It means that, well, I'm really interested in these things because I think this models my mind better than, let's say, drop downs or file systems. And even though they're more unwieldy to represent and and therefore to navigate and therefore not so easy to reason about, in fact, there's a lot of interesting challenges that come with layout and navigation and so on. And I'm interested in that, and having an efficient simulation that runs in the GPU for making this kind of rendering tractable in a kind of more interactive manner, then that's really needed. You really need to have kind of a GPU implementation. Okay, so layout algorithm, good. I'm interested in that. And then I'm interested in the GPU. And I'm interested also in sort of a streaming abstractions on top of all this. And that's kind of a stretch goal. But that means that I obviously don't want to program the GPU directly. I want to have a high-level language I can use, and then I want one that also has some specific, pays a lot of attention to the low-level implementation of the code. And so doing this in purescript basically would mean nothing because we have some WebGL bindings in purescript, but WebGL is not as powerful, for instance, as OpenGL, directly accessing the CPU. So there will still be some differences there. WebGL is evolving. There's WebGL 2, and there's also WebGPU coming out. And there aren't bindings for WebGPU yet that I'm aware of for purescript. So that will come. But in order to also think through specifically issues of, I guess you could say, low-level, efficient data flow programs that do their things across the CPU and the GPU, then basically most of the action, most of the people thinking about these problems are mostly aggregated around the Haskell ecosystem, and few of them exist in the purescript ecosystem at this point. So what does this, and I'm going to probably copy all this and add this to our links. And we're not doing chronofold today, so let's remove this. Okay. So, but still, one thing really interesting here is that we have a JavaScript implementation that's actually based on this GPU utility, and a parallel algorithm of the NBody problem that can be executed in a fragment shader. So I think, hopefully, maybe I can start, if I start being better at understanding these things in the Haskell context, and with also understanding better how those low-level efficient data flow programs look like in Haskell, then I think I'll be better equipped to even think about how to optimize things in the browser. And maybe by that time, WebGPU is a bit more available, and so on. I think right now, WebGPU is only available in a Chrome Canary version, and maybe in some also alpha release for Firefox. So yeah, this stuff is new, and I guess I'm also thinking about maybe preparing my thinking around these things. Okay, so I looked up then NBody GPU Haskell, and okay, I need to give another example of something that was really cool to see, and that's related to my hardware. I have a pretty beefy GPU card, even though my motherboard is more than 10-year-old. It's from 2008. So my CPU is really bad, but my GPU rocks. It's not an RTX, so it doesn't rock as much as that, but it's Titan XP, and so it's an NVIDIA thing, and in the CUDA examples on GitHub, there is the NBody simulation. NBody, where is it? It's okay, NVIDIA CUDA NBody. And so that's the docs of it, and so I need to do GitHub, I suppose, to see the code of it. So that's one NBody simulation for CUDA, and there's an official one. Yeah, it's in CUDA examples. Oh yeah, I remember this thing has been kind of moving around, and it was hard to find it in the latest SDK. So that's a little bit strange, but in an older version that's still online, we have our GPU code and whatnot. So that's all very low level. Using, you would need to set up Visual Studio and, CMake, build all these things, and then we'd have NBody. But we're not C++, so I'm not a C++ developer. I'm not particularly interested in growing my knowledge in this. Let me though copy these things. And that means that what I'm more interested in is seeing, okay, well, is there an NBody implementation that uses the GPU in Haskell? And yes, there is. There's Accelerate, and Accelerate is a suite of tools that are really done to optimize high-performance computing with Haskell. So pretty much the bleeding edge of performance in Haskell. So not necessarily the bleeding edge in terms of APIs, though maybe but I've watched some talks from the developers of this. Actually, I think also Michael Peter-Jones has Simon Peter-Jones has a talk on nested data parallelism, which and does this consider, is this related to Accelerate? Yeah. So, and there's also a talk online about this. That I think is some of the bleeding edge, which is sort of maybe the more theoretical edge of things. But there's a library, and it goes fast, and it's done for high performance computing, and it has an NBody simulation of gravitational attraction between solid particles. And it's supposed to be able to be to offload computation to the GPU as well. So that's sort of what I'd like to explore now. So I never used Accelerate before. I've just watched a few talks on it. I'm, I guess, intermediate level on Haskell. I've read a lot about it, so I think I know more than my level. But in terms of actually coding, I'm sort of entry intermediate, I think you would say. And so purescript is kind of my way of getting into this. And I'm also fairly new to doing GPU programming. I've compiled those NBody examples that come from the NVIDIA SDK, and they are gorgeous. I love those. They're really beautiful, and I want to play around with that. And maybe we could use this instead of, like, for instance, this, which is kind of like the aesthetic that I'm going to be going for. And so we can maybe derive some aesthetic pleasure as well as some theoretical knowledge and coding experience here. So yeah, so you know what? This is a good presentation of where I want to go. And there's a number of things that will come with this, which are more, again, like environment related, meaning tooling and whatnot. I think this machine is fairly well set up already, I think. I mean, I think it has Haskell there, but I'm really annoyed with PowerShell, and so maybe, and I'm not sure about this whole containerization thing, like the whole Ubuntu VM in it. I'm not sure that that's going to be nice for GPU. So we need to find the sweet spot here to do GPU on my particular NVIDIA GPU. On Windows, which I'm not super familiar with because I've been doing OS X. I had OS X as workstations forever, and trying to make and try to get something on screen that looks like a beautiful NVIDIA presentation that's written in C++. And so that's the goal. And I'll break here, and I'll get some food, and I'll be back to do probably some tooling. And if we can get these examples to compile and to run in our GPU, then that'll be great things for first session, but I'm not sure we'll get there. So I'm going to write this as a goal here, run NBody example in GPU. And I'm not even sure whether it says that things maybe on the fly offloaded to the GPU, but it's not clear whether actually this NBody simulation can be offloaded to the GPU or not. So I'm new to that. So we shall see. And we'll explore tangents. That's really nice things to explore there, because in the kind of CPU, GPU world, there's beautiful work done by Colonel Elliott on compiling to categories, which also aims at compiling to the GPU. And that's something that also requires a fair amount of tooling. And it'll be really interesting to think about whether we could even think about such a thing as compiling to categories and NBody physics simulation with this tooling. I have no idea. GPU code generation, right? And then there's this other thing, FEAR, an intermediate language for the GPU programming in Haskell. So that's also adjacent to, and it's really hard to come to get the search results for this. It's not the first time that I have the trouble. Oh yeah, and Julia, there's a good chance that actually Julia is ahead of Haskell on some of these things, because it has a lot of momentum. And I think you are doing conversion for me, and it is the gentleman who developed Lambda Cube, I believe, who does this, and holy moly, this is hard to find. It is FEAR, right? I'm pretty sure. Yeah, here it is. An embedded language for writing GPU shaders in Haskell. And that's also, I think, will be more cross-platform potentially, because it targets Volcano OpenCL. I kind of forget what the deal is, or the dealio is with all of this, but this is a really interesting way also to program. So I'm going to copy these as well in the log, because they're part of the sort of general space that we're looking at here. And that's it for me right now. I'll be back in an hour or so, and thanks for watching.